So welcome, everybody, and to anybody listening from overseas, welcome to Thursday morning. So we're very glad to have Doug Woos here. He's finishing his internship, and he's going to tell us about his adventures with Z3 performance and stability.
All right, thanks, Chris. Again, I'm Doug. Normally, I'm a student at UW, but I'm going to be talking about work that I've done this summer at MSR with Brian Parno, who hopefully is on his way here, and Chris Halbitzel. All right, so I've been working on improving the performance and stability of these SMT-backed verification tools. So examples of SMT-backed verification tools are verification languages like F* and Dafny, and other tools that, like Dafny, compile verification conditions to Boogie before sending them to Z3. These tools are really great. They let you avoid the kind of tedious manual proofs that I'm familiar with from my background using the Coq proof assistant. But they do have this problem where proofs often break for seemingly no reason. So you'll get a proof to go through about your program, and you'll change some lemma that seems like it should be unrelated, or upgrade your version of the tool, et cetera, and suddenly your proof will no longer go through, and you'll have to add asserts or twiddle things around until it works. So this summer I've been trying to answer the questions, why do these proofs break, and can we make them not break? So for this talk, I'm going to start with some background on these SMT-backed verification tools. I'm then going to talk about some experiments that we've done in order to understand sources of instability. And then I'm going to talk about some preliminary work on actually mitigating this instability and improving the situation. So I'll start with this background on SMT-backed verification tools. So the main tools that I've been looking at are Dafny and F*. Dafny has this architecture where it first compiles things down to Boogie, which is a low-level verification intermediate language. It's sort of a relatively thin layer on top of Z3, but that adds some convenient abstractions. F* just ships verification conditions directly to Z3. So I want to go through an example of Dafny. So this is a very simple but complete Dafny program. So this is a method which we've called M for space reasons that takes an integer and returns an integer. It has this post condition, which is specified using this ensures clause, that the thing it returns equals 3 times its input. And it's going to calculate this in sort of a complicated way for the purpose of this example. So it's first going to create another variable z, which is equal to its input plus its input, and then add z to its input again. I think you'll agree that this, in fact, returns 3 times x. So this is going to then ship a verification condition to Z3. And very abstractly, this is going to look like this. So if z equals x plus x and y equals z plus x, then y equals 3 times x. Z3 will say, great, this seems valid. And then Dafny will tell the programmer that the program is correct, and they can then extract it to C# and compile it and things. So in a little more detail, when Z3 sees this, we're setting it these premises and this goal. So the premises, again, are y equals x plus x, z equals x plus x, y equals z plus x. And the goal is proving that y equals 3 times x. But what we're actually going to pass to Z3 looks more like this. Z3 will either tell us, OK, valid or not valid. What we're actually going to pass it looks like this. So we're going to negate the goal. So we're going to say not y equals 3 times x. We're just going to add it to the premises. So what we're actually passing Z3 is just this collection of facts. And then we're going to ask them if these facts are mutually satisfiable. Okay? So if Z3 can find some satisfying assignment to the variables such that all of these facts are true, then it's going to say sat. If it can prove that there's no such satisfying assignment, it's going to say unsat. And if it says unsat, then the goal that we were originally trying to prove is true. Right? So this means that the premises imply the conclusion. There's this unknown option. So if Z3 can neither prove that it's unsat or find a satisfying assignment that it knows is correct, then it's just going to say, I don't know. we see this a lot, all the time in verification tools, and this means you need to do more work in order to convince it, or it's just false. So this sounds great. Why do we have this instability? So when we look at these facts, when they're presented on the slide, these look pretty doable for Z3. This seems easy. In fact, the Dafny program that I showed you compiles to 317K of Z3 facts. I'm just going to tab over to Emacs real quick and scroll through this file. This is at a very small font size. Sorry, but it's really long, so I'm paging through it here, et cetera, et cetera, et cetera. We can go a little faster. Yeah, so that's it. So we're throwing a lot of stuff at Z3, like a lot of stuff. And Z3 is amazing for handling this at all. So it's handling these enormous verification problems. This is literally just that Dafny program that I showed you with the one method M is generating all of that. You can imagine that the complexity grows with real Dafny programs that were, for instance, the Iron Fleet project, which verified serious distributed systems in Dafny. The verification conditions are commensurately more complex. On the verification problems that I've been looking at, Emacs almost always complains about how big the files are. So these are like, on the order of 5 meg to like hundreds of megabytes. And in addition, the problems that we're asking it to solve are fundamentally undecidable. So because we have all of these quantifiers, so many of the formulas that we're passing to Z3, rather than being simple like these ones, are universally quantified. So we're saying for all x, something is the case. This is just undecidable. So Z3 is at a fundamental level based on these heuristics. So, and we have to treat it as this extremely well optimized, but sort of deeply mysterious black box. And this means that these little things can cause it to spin out or fail. So, and we call this the butterfly effect. The butterfly that flaps its wings in Thailand and causes a hurricane in Florida or whatever. So we tried to quantify this a little bit. And in order to do this, I wrote this tool called Mariposa, which is Spanish for butterfly, and is just sort of a pretty word. So this is a tool that will automatically perturb Z3 input. And it works on all of the output generated by Boogie and F star that's then sent to Z3. So I implemented a bunch of perturbations of this input. So a few of them are just changing the random seed. So you can set the random seed that Z3 is going to use. It needs to generate random numbers all over the place in order to decide what branch to take at various places. I can alpha rename all of the variables in a file. So the files that Boogie and F star send to Z3 contain a bunch of function definitions. We can just universally rename those. So in this instance, Z goes to C, X to A, Y to B. We can reorder the facts that we're sending Z3. So in this case, we would just reorder these individual sets of facts. So we're permuting those randomly. We can also reorder the queries. So the Dafny file that the Z3 input file that I scrolled through in Emacs earlier actually had 2 queries in it. So for this method M, it generates both a well-formedness check and the actual implementation. So ensuring that the pre and post conditions imply each other. And a real Dafny file from Iron Fleet, for instance, or from the test suite will have many methods and many queries. So we can reorder these queries that we pass to Z3 as well. So our first sort of research question was, do these perturbations affect Z3's behavior? So we ran this on the Dafny test suite, plus a few individually selected butterfly files that people had sent me, basically saying, I hear you're working on this, this file has weird behavior. We think the answer is yes. We found pretty significant timing variability when we applied these perturbations. And actually, in a few cases, we managed to see completely different behavior on the perturbed file. So files would return unknown when they had previously returned UNSAT or vice versa. So for example, one of the two, there were two sets of alpha renaming perturbations with different just random seeds to the alpha renamer. And these are the timing results. So one is the same as the original file, and then these are speed ups of alpha renaming. Not that it's intended to speed things up, but the time that the original file took divided by the time that the alpha rename file took. So it sort of oscillates around 1, and this could be just random noise because they were run on different machines. But you can see that there are a bunch that are very different from 1. So these are cases where Z3 seems to have been really affected by this perturbation. And the graphs for the other perturbations look sort of similar. So we'd like this set of files to be the beginnings of sort of a standard benchmark for the stability of SMT solvers. We're working on adding some F-star files and files from other sources. So for instance, the Iron Fleet and Ironclad work, or pick your favorite project done in Dafny, Boogie, or F-star. And we'd like to start running it on other solvers as well. So CVC4 takes the same input format as Z3 and is used in some of these, or has been used in some of these tools. So we'd like to compare to CVC4 and see what its stability is like. So now that we've quantified instability a little bit, I'd like to talk about some things that we've tried in order to mitigate instability. Yeah.
So the graph you showed, was that for a single benchmark?
This is for all of our benchmark files on a single type of perturbation.
So 2 samples per file?
So this is one sample. So we run Z3 on the original file and then also run Z3 on the alpha rename file. But each only once.
Each one of those gets you a line?
Each one of the, yeah, and then and then divide the time.
Do you have histograms for say a single example where you do lots of alpha renamings and pseudo distribution?
Right.
I do not. Yeah, those would be worth generating from.
So we have this random seed command line parameter.
Yes.
That we then use to find butterflies.
Yes.
And there we take, that's based on a single file but different seeds. One thing I'm wondering about is, say, the density of the spikes. Right? So if you have few spikes for a given benchmark, then in average it's doing the same.
I'm not sure I understand. So you're talking about sort of looking at the stability of individual benchmarks?
The mean and the variance of the variabilities. That can give
some
idea of how bad.
You did have a perturbation that changed the random seed.
Yeah. And that led to a little less variance than this.
Actually, it strikes me Z3 ought to be impervious to alpha renaming. No? I mean, none of the IDs and syntax nodes are affected by it.
It affects the ordering the hashes.
Well, things are being sorted using names and not AST
node symbols. The symbols are internal, made to atoms, and then the order of those.
Yeah, I mean, there are a lot of ways to slice these data, and we've sort of just gotten started doing that. I have graphs for the other perturbations, but yeah, the experiment where you do alpha renames with a bunch of different random seeds and then see what that looks like would be worth doing.
Yeah, so sometimes I use that to identify what a weak component. So one example of a weak component is integer solver. There's some integer benchmarks. But give it random seeds.
I see. So you write an integer. You write a benchmark that uses this solver, and then you change the random seed and see what that is.
And that shows that internally the solver is getting off.
Sure. Interesting. Okay. Any more questions on these experiments while we're at it? We can also just do this at the end. Right, so we tried a couple things to try and mitigate instability, so I'd like to talk about those. So the basic idea of our attempts at mitigating instability is just sending less stuff to Z3. So again, there's this huge pile of facts that we're sending. And a lot of these tend to be unnecessary. So just in the example that I've been showing you, in order to prove that x plus x plus x equals 3x, Z3 really doesn't need very many facts, right? But we're sending it, for instance, the whole Dafny standard library, which includes, axioms about sets and multisets and maps and lists and et cetera, as well as sort of facts about heaps that we don't need, a lot of stuff. And the nice thing is that we can always remove facts soundly. So because what we're sending to Z3 is just a bunch of these facts, and it's trying to see if they're mutually satisfiable, if we cut out some facts and it finds that they are mutually unsatisfiable, so it can prove false by the conjunction of a bunch of these facts, then the whole set of facts is mutually unsatisfiable. So Z3 does have this facility for generating what are called unset cores. So we could talk about that a little bit. So what an unset core is, so let's say we have these facts that we're sending to Z3, and instead of the facts that we were sending before, let's say that we have this other fact. There's this other thing W, which is equal to x times 2. If you run Z3 in the mode where it will generate unset cores, it will say, okay, these are unset, and the facts that I used in order to prove that it was unset are just these. So if you call it again, excluding this fact, then you should still get unset. So we did an experiment where we generated unset cores for all of this Mariposa data. So we had these perturbed files that were generated by Mariposa. And for this benchmark, we actually included some of the F star files. And we included all of these files where in the original experiment, all of the queries resulted in unset. So if a query doesn't result in unset, then you can't get an unset core because it wasn't unset. So this, we ended up with around 3,300 inputs. So our research question here was, are unset cores fast, and are they stable? So we generated unset cores for all of this Mariposa data. And I already said that, okay. So the answer was that, yeah, they're really fast. We're still not sure about stability. We had this problem where in around 7% of the cases, when we passed the unset core to Z3, we actually didn't get unset back. I'll talk about why that could possibly be in a second.
Did you get SAT?
Unknown, I think. Yeah. Yes, SAT would be disturbing. Yeah, really, we never, ever get SAT, right? Because we always have quantifiers. Yeah. So on average, we saw a 6x speed up, but this ranged from 50 times slower to 100 times faster. So we saw an extremely wide range with these unset cores. And here's what the data look like. So again, 1 would be no speed up, and this is a 10x speed up and a 50x speed up. So we can see that this is sort of all over the place. You can't really see the 50x dips because again, there are 3,300 samples squeezed into this graph, but they are in fact there.
What are the ones on the right? What benchmarks are that?
I'm not sure. Sorry. Yeah, these were, I think something from the Dafny test, but I'm not sure.
This is a 50x speed up, is that what it says?
Yes.
And you said you also saw 50x slowdowns?
Yes.
Tiny little valleys.
Okay.
Right, yeah. It's harder to see a 50x slowdown, 50x speed up, unfortunately. I tried to get the log scale working.
So they're rare.
So like you can see slowdowns like, I think this guy's a slowdown, probably not a 50x one, but I think it's
But
below 1.
It's compared. I mean, what's the probability of a slowdown?
So 6x was the average.
6x speed up was
Speed up,
Right.
but the probability for a slowdown is
say
the number of slowdowns.
I see over the, yeah, I'm not sure.
Which looks like less than 1%.
Yeah, I'm not sure that we're going to be able to see that on this graph, but not very many of them slowed down. That's true.
Were you running with a like huge timeout, like, so that you were letting them run up?
Yeah, 5 minute timeout.
5 minute timeout on each one.
Yeah.
I see.
And they all use.
Sorry, on each file, though, not on each query.
And these all use quantifiers pattern.
Yeah.
So how are the unknowns shown on this graph?
These are only the succeeding
Was
cases.
came back on
Yeah.
UNSAT. Okay.
Yeah.
So, big source of variations would also probably aren't quantifiers. Did you look at quantifiers?
Yeah.
Yeah, all the files have quantifiers.
Okay, but you didn't do anything. Did you do anything explicitly with sort of like you did this alpha renaming, but did you do anything to explore sort of the treatment of just the variation there?
I'm not sure what you mean.
Well, there's many different ways that C3 handles quantifiers.
Yeah, I mean, and with patterns, the quantifying instantiations depend on the set of ground terms that are present in the perturbed state. And then
Right. So I just was wondering whether there was anything one could do to separate out, that.
explaining.
Yeah.
I always figure that all of the the reason that these take so long is always quantifiers. There are these a lot of quantified facts.
I guess what I was
do end up
asking is
matching.
like a correlation between the use of certain types of quantification, maybe, and the variability.
Yeah,
So-
I'm not sure.
It's their heuristics for choosing the pattern, so we could try to tweak those heuristics and see if it changes.
With things like for all x, for all y, blah, would its behavior change if you change it to for all y, for all x, blah? I don't know.
But listen, so you don't use NPQI.
No. Yeah. So it's all pattern based.
Which narrows down the kind of whatever reasoning.
Yeah.
And then it really depends on what kind of terms happen to be available in the soup.
Yep.
In theory, you can do profiling and saying, are there particular quantifiers that seem more problematic than others?
Well, and in practice, that's how we end up debugging these files.
Yeah, so there's this profile.
Yeah.
Yep.
What would
So, which we tend to use on individual cases, but Doug didn't try it on. So if there's some guy that's the bad culprit across large swaths.
Right.
the data mining.
Yeah, although it could be worth exploring. Like it is possible that maybe the Dafny standard library has some particular quantifier that's really bad news. So when that gets included, so that would be surprising because I think we would have noticed it. But.
Quantifier, which was really good news because at some point there were inconsistent axioms.
Right. I'm pretty sure we don't have those, or Bruce would go through a lot of.
About the timeouts again. So you said that 5 minutes per file, but
yes.
But then is Z3 not using the timeout per query rather than?
This is the
you
this is the
enforcing
hard
timeout?
timeout, like top level timeout.
That your tool was enforcing button playing. Like if the file took more than 5 minutes, it would just stop.
No, this is the there's a dash like capital T option to Z3.
I see.
Yeah.
Which
I believe that's file. Maybe I think it's file because when we time out it takes around 300 seconds.
and you have more than one check site per file.
Yeah.
Do you know for the big spikes something about the size of these files compared to?
So I assume that any of the big spikes are going to be things that took a while originally.
In terms of file size?
I don't know. I mean, lots of check sets, but yeah, I'm not sure about like relative to the baseline.
13 or 14 centimeters.
But like there are these files do themselves range pretty widely in size. So and in particular in the time it takes Z3 to run normally, right? So some of these took only a second before, or half a second. We're not going to get 100x speed up on those because there's just not.
Right.
Yeah.
So when external replays on set cores,
Yep.
it always it always does it in style where it's one file per check set, because it has to, it's got a large context, it's got a query that it wants to ask.
Yep.
It's going to prove that context with respect to some UNSAT core.
Yep.
Fresh each time for each check set.
Yeah, I do that. So I label each assertion uniquely and then get UNSAT cores for each check set and then prune based on that. So I think it should be equivalent. But, yeah. Okay. Right. So why are we sort of teased this a little bit in that discussion? But why do some UNSAT cores not end up returning UNSAT? We think it's because of quantifiers. So or because of quantifiers and patterns. So quantifiers are hard. How we address this is with patterns on quantifiers. So these are annotations on quantifiers that tell you when you should instantiate that universal quantifier to a particular value. So we're going to write this like this. So let's say we have this collection of facts. Not too important what the details are. These are just uninterpreted functions that are applied to particular values. And we've got one of these facts is quantified. And this notation in the squiggly brackets means that there's a pattern on this quantifier. And this is kind of a weird pattern. So in this case, we're saying, for the purpose of this example, right? So this is a pattern on h of x, which means that Z3 will only instantiate this quantifier to a particular value at a particular value x if it sees h applied to x somewhere else, right? So you would never actually see this pattern because h of x doesn't actually appear in the quantified formula, but for the sake of example. So in this case, let's say we try and find an UNSAT core for this set of facts. The UNSAT core we're going to pick out is this. Why? Because, well, we have f of y, and we're trying to prove, and not g of y. Well, if for all x, f of x implies g of x, makes this whole thing unsatisfiable, because we have f of y, so g of y. But if we tried to replay this UNSAT core, Z3 would return unknown, because we no longer have this h of y fact, and that's the only reason that this quantifier gets instantiated at y.
So I was talking to Christoph about this a couple days ago, and he said this is a bug.
So the UNSAT core should include
UNSAT core should have included the first one as well.
That'd be great.
Yeah.
And he said he was going to fix it.
No. He's not. He's not a bug. So you twisted his arm. Yeah.
No, I didn't. I mean, you should, okay, I'll share with you the Slack thread. But he says he's going to fix this and put h of y in there.
This may or may not be fixed in future versions of Z3, depending on which of the Z3 authors gets to it first.
Man, how would you fix it? What's the fix to it?
I guess
What does it mean to fix it?
Well, I guess you see how this thing was instantiated, what caused it to be instantiated, and you
But
see
that's a
which.
subterm. Now the subterm has dependencies. How are you going to track those dependencies efficiently?
I don't know. But so the end of that conversation was that he said he'd add an option, so that if the option was enabled, he would report h of y also. And I thought that was a fine idea.
Did you put him under some magic spell?
We just assume the Z3 guys are really good.
Okay, but carrying on, do you have the mitigation for this?
Kind of. I mean, basically no, but yeah, kind of. So this is why 7% of these lead to UNSAT. So part of the why we did this experiment was that we knew that this problem could come up, and we wanted to know how often. And the answer, at least on this set of data, is 7% of the time, which is a little, I guess I would say, discouragingly high if we do want to have this sort of hint facility work in general. So it would be great if Christoph added this magic option to C3 that would track this. But the speed up is clearly promising. Recent versions of F star include this hint facility. Yeah.
So we know that this is one source for why an UNSAT course may not be replayable, but we don't know that it's the only one.
Yep, that's true. Yeah, I'm not sure. The thing, getting at like why answers is tricky.
And actually, I mean,
I have a data point though.
Yeah.
Because I'm working on a different tool that uses only decidable theories. So it has quantifiers, but it has to be in a decidable fragment. And it never happens that an unsat core is not replayable. So in other words, with quantifiers or with theories or whatever, but if you don't mix them in an undecidable way, so it could be there are things like interactions of quantifiers and arithmetic and so on. But if you're sitting in a decidable fragment, the unsat core is always replayable.
I mean, the other, I guess, kind of piece of evidence that there is something going on here with quantifiers is that, like, while it's true that sort of random perturbations cause Z3 to be unreliable, less so than the unset cores do, right? So, like, the alpha, like, there is some just noise because, it's heuristic, so, like, shit happens. But, like, the unset cores are, the 7% number is much higher than that, which suggests that something funny is happening.
The thing that I'm puzzled by is that the kind of examples that we come up with to illustrate that this is possible, like the one that you did, that you had, generally feel a bit unnatural, right? So how could it be that like 7% of the programs that we're actually verifying have these weird quantifiers around?
I blame F star and F.
It sounds like, Nicole, it's primordial soup theory, right? Where you're saying
no,
you,
but the slide was-
you have a bigger soup of terms. You have
That's what his slide was illustrating.
But like F star and Dafny, so one example could be like we end up with triggers on like stuff like the typing judgment and stuff. So like if we're not getting those, I'm not sure. And there are also quantifiers without patterns, so that's where we could be getting the ground terms from. I'm not sure. It's true. I would love to come up with a less sort of contrived example that seems more realistic where this happens. And it might be worth looking at one of the smaller files where this happens to try and figure out exactly why it's not working.
But the efficiency thing, I mean, if usually when this happens in F star, it's a symptom of an unstable F star proof to begin with, and typically, I end up fixing it by rewriting the proof in some way, and then the unsat core replays and everything is good again. But
how would you characterize an unstable proof?
when the unsat core is not replayable.
But that's not a definition.
The definition by 2, maybe?
So I said, I write a proof in F star, it succeeds. I extract an unsat core, I try to replay the unsat core, it doesn't succeed.
Yeah.
So at that point, I'm like, something's up with this proof.
But you write a different proof and then it succeeds.
Yes.
But that could be just butterfly.
No, and then the unsat core succeeds for that proof.
Yeah, that's what I'm saying. For some proofs it does, and some proofs it doesn't. But is it just random? Is there something about one proof that's different from the other? That's
It's a completely different proof. I end up doing the proof by writing a proof term and explicitly abstracting and move into a different mode of F star. I like write a constructive proof typically, as opposed to writing an SMT proof.
So that's stable because you're not asking Z3 to instantiate quantifiers then. Or
yes, effectively. So I'd like to know.
because this is what I was saying before. If you just don't ask Z3 to instantiate quantifiers, then it's stable.
Yeah. So what I would like to know at that point is to say, yes, I believe this proof, this particular quantified instantiation that I used the first time, it's unstable. It's unstable because it relied on some patterns that were not in the unsat core that was reported by Z3 initially, and I don't mind if that takes very long.
But that's the case that we're talking about here, right? Where you had not a pattern that wasn't in the unsat core, but a term that wasn't in the unsat core.
A term that triggered. That's right.
Yeah.
That's right. And I don't mind if Z3 takes very long to report which term that could have been.
So that would be a version of Christoph's magic feature.
Yes.
Maybe be easier. Yeah. Right. So as Nick suggested, F star has this sort of hint facility that uses these unset cores. But we'd like to do a little better than unset cores in some ways. So one problem with unset cores is that they have this unreliability thing. Another problem is just sort of fundamental. In order to get an unset core, you have to run Z3 on a file that's unset. So is there an operation that we can perform just on this set of facts without running Z3 that will get rid of some of them soundly in the way that unset cores do? As you might guess, the answer is yes, since I asked the question. So there's this algorithm called sine qua non, which was developed in the large theory theorem-proving community, which exists. So this is these very large sets of math facts of up to like 3 million facts and then you'll try and prove an additional thing. So let's say you're trying to prove something about like an arbitrary group, and you have a bunch of group theory axioms. Instead of just throwing all 3 million of these plus your additional fact at a solver, you'll want to select some of these premises to throw at the solver in addition to this fact. So this problem is called premise selection. Apparently, it's also called cone of influence in some verification contexts. But as far as we know, this algorithm hasn't been used really in the program verification context. So we've been implementing it for Z3's input files. To go through what this looks like, the idea is that we've got a bunch of facts. These are the same ones that I showed you before. And there are some symbols that are in common between them. And we're going to use those in order to select which of these facts we should keep. So first, we're going to look at the symbols that are in each fact. So these are just sets of symbols. So the top one was applying h to some variable z, so it has h and z, etc. What we then do is view the facts as a graph where the facts are nodes and the edges are common symbols in between these nodes. So in this case, those two facts share the symbol G, etc. We then look at the goal. So this is where I've been describing what we pass to Z3 as sort of this pile of facts, but Dafny knows which one of those is the goal, the actual verification condition that it's trying to prove. So we look at the goal, and then we take the connected component of the goal in this graph. Then we can just include those facts. So we just have those. So we managed to get rid of this h of z fact that we really shouldn't be including.
That's basic slicing.
Yeah. It's just a program slice.
But the sign selection is not basic slicing.
There's this common term thing.
Yeah.
Yes. I'll get to that a little bit. We'd like to do a little better than what I showed you because we'd like to handle quantifiers in a smarter way. So we only want to include symbols bound by a quantifier if that quantifier could actually be instantiated at runtime, because otherwise it's really irrelevant. So what we're going to do is we're going to statically over-approximate Z3's instantiation of these quantifiers based on their patterns. And we're going to do that by just ensuring that all symbols in the pattern could actually be generated at runtime. So I'm going to go through a worked example of what sine qua non looks like on a set of facts. So the set of facts is going to be this one. So we have for all x, h of x implies g of x, and this has a pattern on h of x. For all x, f of x implies g of x. This has a pattern on f of x. And then we have f of a particular variable y, and we're trying to prove g of a particular variable y. So we're going to track the symbols that appear in each assertion and the quantifiers that we've seen so far. So we're going to look at the first fact. This fact is just an outermost quantifier, and we haven't seen the symbol h yet, so we're going to add it to our list of quantifiers. So the fact 1 contains this quantifier. We're going to do the same thing with fact 2 since we haven't seen f of x yet, since we haven't seen f yet. So it's quantifiers list. Hello? Okay. We're seeing this fact. We find the symbols that aren't bound in this fact. We find 2 of them, f and y. So we're going to add those to our set of symbols, saying that they're from fact 3. And now that we've seen fact f, we have tracked that there's one quantifier, symbol F. There's one quantifier that's waiting on symbol F, and it's the second quantifier. So now that we've seen this, that pattern could be instantiated at runtime. So we actually look at the bound expression, and we find the symbols that are in that bound expression. So now we can add, so we're looking at that quantifier, and we can add its symbols to our list of symbols. So now we've recorded that fact 2 contains the symbols F and G, and we can get rid of that quantifier because we've already processed it. Finally, we look at the last fact. This has this G and Y. Since the only quantifier we have is waiting on H, and we still haven't seen H, we don't have to worry about it, and we just add those to our list of symbols. And then we do the same graph algorithm that we did before in order to find the facts that share symbols in common with the goal. So, and in this case, we can get rid of this fact 1 that just has this pattern on H of X. So we have an implementation of this. We've implemented it as a preprocessing pass that's actually part of Mariposa, and it's totally unoptimized. It parses the SMT2 file, runs this, and then spits it out and passes it to Z3. So excluding the time it actually takes to do this preprocessing pass, we get a 2x speed up on Z3. This is kind of unfair because this means that Z3 doesn't have to reparse all of these facts. So just on slow query, but we figure that parsing overhead is close to constant, or at least isn't a huge part of Z3's time on large files. So on queries that were slow in the original execution, we get around a 1.4 to 1.5x speed up.
Could that be regression to the mean? In other words, pick the slow queries, randomly perturb them with alpha renaming, and on average they'll be faster.
That's interesting.
I don't to the mean.
Yeah, I don't think they'd be 1.5x faster. They might be faster. Yeah, that's an interesting point, though. And this is what the results look like graphically. And the minimum was that it was 3 times slower. And the maximum was 6 times faster. So again, there's variance, not as high as the UNSAT core case, but it doesn't uniformly speed everything up.
And you don't get any additional unknowns by doing this.
We do, frustratingly. So there is this, and I looked into one of them, and it's a case where we're killing 2 facts that the axiom profile assures me are just never being triggered at runtime. And if you remove either of those, then it breaks. Yeah.
Pure butterfly effect.
Yeah, exactly. And similarly, there are some that we fix. Although I'd love to, count those as a success. I don't know that I can, in good conscience, do that. So we're currently working on adding this to Z3 as a tactic. So Z3 has this tactic interface that lets you process the goals before you check for satisfiability. This will have, one more thing on the original version that isn't in Z3. There are actually some goals where even the totally unoptimized one, if you run that and then run Z3, that's faster than running Z3 on the original file, which is, I think, encouraging. And this should be significantly faster than that because we don't have to parse and reparse, and also because it is implemented in C++ versus F#. And our hope is that Boogie and F* can just always use this. I think this should be an improvement, and we're hoping that it might actually be useful for other verification for other tasks in Z3 as well. So as Nikolai suggested, there is this, the actual sine qua non algorithm tries to be a little smarter than this. And we think that should be useful for our purposes as well. So what we find is that there are certain symbols that appear in a lot or even close to all of the assertions. So a lot of the assertions that or almost all of the assertions that we're getting rid of are just quantified on the outside. So we never have to look at them. So for instance, the typing judgment for Dafny or F* is often included in many of the assertions. So, and we think that by not including, by not following those edges in the graph that are based on just the typing judgment, we should be able to kill more assertions, possibly at the cost of some stability. So you could imagine running the aggressive version of this in parallel with the version that should be totally safe. We're still looking into that. So as some additional future work, we'd like to do more measurements on this large data set we have. The data set is close to qualifying as big data. It's like 700 gigs or something. And we'd especially like to look at more sort of stability stuff. We'd like to compare Z3's stability to other solvers, in particular like CVC4. And we'd really like this eventually to become a standard benchmark for solver stability. So in conclusion, I've run some experiments. I've generated this data set perturbing Z3 input files. I've looked into the instability of Z3 and its performance on UNSAT cores. I've produced a couple of tools. So there's this Mariposa tool that perturbs Z3 input files, and I'm currently working on, and will hopefully have done by end of day tomorrow when I leave, an implementation, a basic implementation of sine qua non for Z3. So I'd like to thank my mentors, Brian and Chris, and all of you for coming, and I'm happy to take any more questions. Unless we got to all of the questions already.
So let's see, so at this point you don't have data on, let's say you do slicing and you don't do slicing. What's the variance of runtime? You know, what's the amount of butterfly effect on the two versions?
Right. Yes.
But that's part of that's future work.
Yeah. And actually, I should have, I have a lot of that collected, right? So I don't have, I have sort of slicing it the other way. So we first perturb and then slice. I don't have slice and then perturb. Yeah, but it would be interesting to look at the amount of variance before and after slicing, and also with on-site course for that matter.
Thanks, Doug.
Okay, thanks.
Yeah, thanks.